All right, so we're going to actually now apply essentially these time domain specifications that we talked about, and specifically to see for the following spring mass damper system, will we be able to hit these design specifications? So, can we have a maximum overshoot of less than 10%? Can we have a peak time of less than 0.5 seconds and a settling time of less than 2 seconds? So, again, what are we talking about here? So we don't want a huge overshoot, which makes sense because if I'm looking at my spring mass damper system, let's say again, like the idea of, again, a suspension, I can't have this mass overshooting the position. I might want to kind of hit that peak time quickly because, again, I want the response to be robust and responsive. The settling time too, I want to be at that equilibrium position. I don't want to be bouncing and oscillating forever. So that's kind of the idea of these specifications, depending on, again, what you need for your particular system. So here, our mass is 2 kilograms, spring constant of 200, damping coefficient of 8 Newton second inverse meters. And we want to be able to see if we can hit these metrics actually. So for our system, we want to see if we can hit this rise time, maximum overshoot less than this, and a settling time of less than this. So let's go ahead and let's see. So first of all, let's go ahead and define some of the values. These are some functions. We can define essentially our mass, our basically damping coefficient, and our spring constant. Assume again u of t is equal to 1, just a step function, unit step function. This will be essentially the response of our system. And now we can go ahead and we can see and calculate some of these parameters. So let's look at the steady state value. So steady state value is 0.005. Again, I can choose to plot y of t from 0, let's say from 0 to 10. I want plot range all. And instead, let's go from like 0 to 4. So we see more oscillations here. Again, this is our system. So we see an overshoot, and then we see essentially that value. So we can calculate, so we know that's our steady state value. We can figure out, or we can find essentially the root. Let's say, actually we can just calculate here. Now remember, this is very important. This, we need our t to be greater than 0. It's the first, right? The peak time is going to be the first value here. So 0.32. And we can actually see we're not even capturing it. Because for some reason it's seeing negative. Again, it's having trouble finding it. So what we're going to do, actually, I'm going to take my find root. So kind of just like we did over here. Peak time. Let's go over here. I see. So let's solve here. Yeah, so we can see. You can see it's really having trouble, but it's having trouble because, again, we have lots of these cosines and sines and then the exponential. So we actually see that value here, but we can also say, actually we're going to calculate in just a bit. We can actually look at here. This is going to be, if we were just to kind of plug and chug and go our way, this will be our TP, so that's our time value here. So remember, we're putting in omega. So we've already defined, and actually we can kind of see that here. We have our relationships between those values. I want to go and let's just continue with this for a second. So we see that negative value. Now that we have TP, though, we can go and do the same thing where it's we can find out what's that maximum overshoot. So what's the value at TP minus this? We can kind of see that maximum overshoot, which makes sense, right? A value of about 0.5 because we're kind of hitting this value right here. So we're seeing this significant overshoot, right, from the steady state value. We can go ahead and try to find that rise time. So 1.01, right, times the steady state value. And we can kind of see, actually, that's giving us our settling time. So let's actually find the rise time. So if we're doing 0.005, I'm sorry if you're getting dizzy from these things. But let's start at 0.05 to 10% of the maximum of the steady state time. We can even do 0.05. Then we can even do starting here. See, now this is a little interesting, but are we actually hitting that root here if we're starting? So for example, we're steady state, and we can always double check the value. So one quick way you can do it, and again, I know this may be tedious and you may want to just do, but I always like to calculate it. T goes to here. So that's 1% of it. Excellent. What about here? We can use 0.01. So see, this is where you have to be a little bit careful. You see the value kind of switches, and it's just kind of depending where it gets stuck. So it's good to verify. And it's good to look on the plot too, because we're probably going to get the same answer. However, and you can see, right? Numerically that makes sense, but if we did this, are we going to get the same response? See, so you have to actually do this time minus this one. So that could be essentially that rise time here. So we got to be careful. We can go ahead and we can actually solve because, or we can rearrange essentially and solve for our omega and our zeta and everything else. So you can solve for zeta right now because, and honestly, your omega n, right? And you can confirm it. One way you can do it, generally speaking, is as follows. So for example, I'm going to clear omega n. I'm going to clear zeta, and I'm going to clear sigma. Let's say we didn't know, or you're not familiar with the spring mass damper system. Omega. I can go ahead and actually solve for it by kind of normalizing and equating the expression. So for example, if we have this general expression that's written in terms of omega n and zeta, I can go ahead and say, well, make this expression look like this expression and basically normalize it, right? So here, the big difference is I need to get rid of m in the particular example. So normalized by the coefficients, and then you can now see I have my normalized. This is the standard notation. This is the other standard notation, and we can go ahead and solve for it. There you go. You could also just solve, and you kind of know. Now remember, zeta can't be negative, so we know essentially it's this expression. We can also solve it here, and we get our omega, our sigma, our zeta, and our omega n. So it's a nice way, if you know the plant function, you can kind of go ahead and calculate those things. So I can go ahead and define. So for example, if I want to kind of verify some of my numbers from my expressions where I calculated explicitly, and one of the things we didn't do, one of the hard things to do with this one, we also need to do so for me, I look at it and I think I'm still seeing, I may want to start searching at like 2 for like the find root. So that works. What about 3? What about 4? So see, it's giving me an error there. So maybe that, but now we need to compare it to this is for the rise time, 0.99. So see, I need to decrease a little bit. How about 2.5? So see, 2.3. Doesn't like it. How about 2.1? So the rise time could be this. So let's go ahead and let's double check it. Or excuse me, not the rise time, settling time. I'm always going to make those little notation errors. Hopefully you'll forgive me for that notation. So if I want the peak time, I just need my omega, and I'm just going to plug that in here. If I want my maximum overshoot, it's just a function of zeta, which is 1/5. And, oops, excuse me, multiple things going on here. If I want the settling time, I need to do zeta, and I need my omega n, which is 10 right here. And then finally, I can look at my rise time, which is zeta, and a function of omega. So actually you can kind of see here, or actually I can just do it as tr function, excuse me, omega n is just going to be 10. Tr fun. There. So I'm going to go ahead and take these values and let's kind of look where we were working with up here. So let's go ahead. Let's kind of see what we got. So TP Fung, that looks good, right? What about our maximum overshoot? We calculate at 52. We see it here at like 52-ish approximately, but different, but it's kind of what we expected. The rise time, what was our rise time? 0.12, 0.18, not too bad, right, for an expression. And then finally the settling time, 2.23. We're doing pretty good. So this is a good, I'm going to save this notebook. This is a good, nice little video. This is a good way to kind of correlate the two. So again, you don't have to remember those functions, but you could just go ahead and calculate it out. But what was the point of all these calculations? Well, it was to make sure we hit those design specs, right? So what was our specs? So we need a rise time less than 0.8 seconds. Made it, check mark. Maximum overshoot less than 15. Uh-oh, that's 50%. That's not good. We also want basically a settling time of less than 10.1 seconds. Oh yeah, we made that, right? So was that it? Rise time, maximum overshoot, and settling time. So that was our problem. So we fail this. So again, overshoots are really bad because again, you can damage that system. So this is not acceptable. But does that mean we fail, or that, okay, we can't do anything, or, that's it? We just have to kind of start from scratch and guess again. What are the parameters? No, we have to figure out where we're failing, where we can kind of see where the fail is going. Let me rephrase that. What metric are we not hitting? What are the parameters that we can tune? And then really importantly, we have to make sure when we tune those parameters, we're not changing any of these other. Because you can see here, there's a lot of, if you change omega n, or you may change zeta, you're going to change a lot of these values within here. So we have to be careful. So what we're going to do next time is a more general approach to where our poles have to be. And we're going to define essentially that region, that Venn diagram where we satisfy all the conditions. So we'll do that general approach next time. We'll plug in and we'll see where we can actually tune this system and how it correlates to physical parameters. And we'll see you then. Thanks.